Okay, I did this wrong. Okay, but I will start now. Okay, hello everybody. Welcome to MAPRG. As you can see, I'm here. Dave is remote, joining us from the middle of the night, I guess. So thank you for being here. And we have a packed agenda, so we will run very quickly through the chair slide and then just start with the interesting part. Next slide. Are you running the slides at the moment, Dave?
So we're at Notewell.
Yeah, so this is an IETF group. We're a research group, but we also have a Notewell. It still applies to you. Also, if you go on the next slide, this session is recorded, so please be aware of that. Next slide. Please also be aware of the privacy and code of conduct. It also applies to IETF sessions, and it's always good to be nice. It's a very short summary. And yeah, this slide is just explaining what the difference kind of is between the IETF and the IETF, but you can read it on your own. Also, the deck has a couple of useful pointers if you need links to the material from today or our group in general. Please join Meet Echo even if you're in the room, because that's our blue sheets. So you want to be recorded in the blue sheet so we get the right size of room next time. And you also needed to join the queue, of course. We said this already. Yeah, please also wear a mask, speak clearly, and be friendly. And that's our out-of-date agenda that I didn't manage to update. So what's missing on this agenda, and that's why it's packed, it's like we have two little nice heads-up talk. Both of them are 5 minutes. We squeezed them in somewhere, and you can check the agenda on the internet because that's updated. But we go immediately to the first presentation. Yes.
So is Marcin local there, or is he remote?
He is coming to the mic, yes.
Oh, great, thanks.
Yeah, you actually can request, or like, can you transfer the control over to Marcin?
I think he has to be in the queue, right?
There are multiple ways. Can you request it? Can you request it again? This other one? Maybe the other one. Now you have to.
There you go.
And now you should have control. Perfect.
Great.
Go ahead. Oh, that's maybe not on. It might be not on.
Okay, yeah, now you can hear me. Awesome. Okay, so hey guys, I'm Marcin. I'm a PhD student from Freie Universität Berlin, and I'm presenting today, but this work was possible also because of my great co-authors, Pujan, Raphael, Jonas, Thomas, and Matthias. So before we jump into the results, I want to make sure that we're all on the same page when it comes to the quick handshake process. So let's start with the basics here. So before Quick, we had HTTP over TCP. And this means we had the TCP, the TLS, and the HTTP handshake, which resulted in at least 3 round-trip times. Now with Quick, the design goal here was that we reduce this round trips to exactly 1 round-trip time. So as you can see, the client basically sends an initial message, the client hello, the server responds with its initial message and the handshake message, and then the client confirms with X. What is important here is that the second design goal was also to reduce amplification. So Quick is based on UDP, and this makes this protocol susceptible to reflective amplification attacks. And this is why the server is only allowed to respond with 3 times the bytes it originally received from the client within the client hello. So the client hello here is not a small packet like a TCP SYN, but it's actually around 1,300 bytes. If the certificates, for example, are way too large and the server needs more data in his handshake messages, then the server has to wait for the acknowledgements from the client and then send the rest of its handshake data. So what then happens is a so-called multi-RTT handshake. So this means we do not have the one RTT, but actually an inefficient multi-RTT handshake. And if you ask yourself, okay, so why is there a lot of TLS data? Well, we have a lot of, first of all, we have the certificate chains. So we do not only have one certificate, but actually multiple certificates. And each of the certificate actually has, for example, the key, which can be very, very large. Think of RSA, for example. Also, we have the subject alternative names field, which can consist of a set of a lot of names, especially in the case of CDNs. So today I want to talk about 3 findings from our paper, where we will talk about why hypergiants purposefully ignore actually anti-amplification because of a trade-off that we observed. We'll talk about how TLS data still interferes with the quick handshake performance. And in the end, we will also talk about incomplete handshakes, which resemble amplification attacks. So this is MAPRG, so we have to talk also about our measurement methodology. We used open source tools to perform active scans. And we started with the Tranco 1 million domain list. And for these domains and the redirects, we checked whether they support the conventional HTTP over TCP. And if they do so, we also parse the TLS certificates. For each of these names, which supports or is reachable with the conventional protocol, we also checked if it supports quick. So here we did the complete handshakes that we just saw in the beginning. But we also did tested the incomplete handshakes, which, as I said, resemble more the reflective DDoS attacks. Now, while performing the complete handshakes, we did not only observe which services are reachable with quick, but also classify the handshake. So again, we have the optimal 1 RTT, which is basically the handshake that we want, that was designed. So 1 RTT, and we are below the amplification limit. But also, there's also the retry case, which is less efficient, but still a great option. However, there are 2 things that we do not want, and this is the unnecessary multi-RTT handshake, and also the amplification case, which is basically not compliant with the RFC because it exceeds the 3x anti-amplification limit. So what did we find? Overall, what we saw is that 1 RTT handshakes are very rare. So in this plot on the y-axis, you see the number of quick reachable domains that we saw, around 250,000. And around 60% actually were amplification handshakes and around 30% multi-RTT handshakes. Now, what you see on the x-axis is actually the client initial size that we used. So we started with a common size of 1,350. So this is a default used by Firefox. And then we moved to the left. So this is more the size that Chrome uses, up to the minimal size of 1,200 bytes, but also went to the right, which is basically limited by our MTU. And the picture is almost the same. So we had a couple of unreachability issues on the far right, but overall, we see a lot of amplification and the multi-RTT handshakes. Now, in the next 2 points, we'll basically explain why this happens. And we'll start with the red bar. So why do we have amplification, and how bad is the amplification? So here you see that for all the amplification handshakes, you see the amplification factor. And what we found is that usually the amplification factor is not larger than 4x. And we looked more into the details here and actually found out that a lot of these handshakes were completed with Cloudflare. So we talked with them about, and they were helpful and explained to us why they actually have this 4x amplification. And this was a design choice. So overall, in CDN deployments, the quick server, which completes the handshake, and the process that has the TLS material can be 2 different entities. So, and this actually can lead to delay, which overall can have a negative impact on the client RTT estimation. Let's take a look what I mean by that. So overall, the client, again here, performs the client handshake, and the server responds. And before we had 1 initial message, which contained the ACK and the server hello. But now what the CDNs now tend to do is they send the initial packet with the required padding instantly. So this allows the client to have a good RTT estimation. And then, as a subsequent process, they communicate with the TLS third store, which introduces a delay. And then they prepare the second initial packet. Again, they add the padding, and then they send this second packet. So overall, we see that, that we have this delay. And if the initial message would be sent coalesce, we would have the delay for both. But here, we just have a delayed server hello and not an ACK. So overall, the instant ACK prevents inflated RTT estimates. This is great. However, with two padded initials, we have the slight amplification of 4x. All right, now let's talk about the TLS data and why we have multi-RTT handshakes. So this is basically the orange part. And there are retry tokens which could also cause multi-RTT handshakes, but the majority, at least for the handshakes that we saw, are usually caused by TLS certificates. And that's why. So we took all the multi-RTT handshakes and sorted them by ascending by the total UDP payload. That's the x-axis here. And then we visualize here on the y-axis the bytes or the TLS payload. And as you can see, in 87% of the cases already, the TLS bytes exceed the 3x limit. When we then add the remaining quick bytes, like headers, padding, and so on, we're far worse. But overall, the main contributor here is TLS data. So we wondered, why is that? And for that, we looked into the certificate chains. And in this plot, we show the non-leaves. Overall, we start with the Cloudflare non-leaf certificate, which is around 1,000 bytes, and it's used to sign 61% of the quick names that we saw. And the median leaf size is visualized here in the yellow bar. So overall, if you visit a Cloudflare hosted site, on average, the certificate chain will have around 2,000 bytes. We then also visualize the worst case. So in the worst case, we saw for this certificate chain around 3,500 bytes, and show here also the common amplification limits with two vertical lines. If we show all the certificate chains that we saw, so this is basically the top 10 here, we see that on average, the median chains are very likely to exceed the common amplification limits. And this is just the third chain. So, So the good message here is these top 10 search chains are used to sign 96% of quick domains. So this means if we have a change here, which would improve the performance, we would have a massive impact on the quick ecosystem. So how do we compensate for such large certificates? Well, there are currently two options. We could, for example, move from RSA to smaller key sizes, for example, elliptic curve. And the other thing would be, for example, the certificate compression, which would compress the certificate chains during the transmission. However, we saw that many clients do not support this. All right, let's quickly end up with the last finding, incomplete quick handshakes. So what do we mean by that? And during incomplete quick handshakes, the client only sends exactly one packet. It's the initial client hello, and the server responds. And now the client does not react, no acknowledgements. So the server assumes the packet is lost, resends it, and no response. So the server continues, and this can probably lead to really large amplification factors. So the thing here is that these incomplete handshakes occur during reflective amplification attacks. So this is why these retransmissions must also be subject to the anti-amplification limit. So we checked whether implementations in the wild really respect this. And one of the implementations that did not was actually the implementation of Meta. So what we did here is we scanned the POPs that, which are usually identified by the /24 prefix of Meta. And for each aggregated by each host octet. So for example, in this plot, you see that all IP addresses that end with .63 on average have an amplification factor of 30. Now, if it comes to meta, usually if the host looked at the 63, the service behind it is Instagram. So we had also, we saw that specific services were more likely to show high amplification. And we also talked with Meta, and they were already working on another issue, and coincidentally then this actually fixed this in, well, does it work? Yeah. So between August and October, we saw a fix. So before we had amplification factors on, up to 30, and now we have amplification factors around 5 for incomplete handshakes. So overall, way better, but still we are over the anti-amplification limit. So here we saw that basically large TLS data leads to large retransmits because we simply retransmit the data that we have. And respecting the anti-amplification limit decreases the chances of loss correction because we have not so many resends that we can do. And overall, this leads to one of our open challenges that we saw, how we actually deal with packet loss during the handshake process in a secure and efficient way. And if you're interested in that, I will talk tomorrow at a quick working group about more challenges and possible solutions. So overall, to conclude my talk, we saw different points to the different results to the TLS certificate ecosystem, which saw that the TLS configurations have now a direct impact on the transport layer performance, so on quick. We saw that if we use elliptic certificates, chains might be, could get way smaller. I think this is already known, but still it now affects the quick handshake process. And up to non-leaf certificates would have beneficial cascading effects. Now, if it comes to quick deployments, we saw that we have the design goals of 1 RTT and the anti-amplification limit. Unfortunately, because of specific deployments or implementations, these design goals have not been met in the wild because of trade-offs usually between the space efficiency and delays that could occur. Also, in the last step, during the incomplete handshakes, we saw that padding and retransmissions can significantly worsen the amplification factor that we observed. And with that, I'm happy to answer your questions. As a last step, maybe a little bit of advertisement. During the last IETF hackathon, we implemented actually a tool which performs for any domain that supports Quick exactly the classifications that I talked today. So yeah, thank you.
Thanks a lot. I guess you can leave the queue and we can have Brian. It's fine. You can also stay. No, stay here, but you can leave the online queue.
Okay.
Hello, good morning, afternoon, evening, whatever it is there. Thanks for the talk. This was really awesome work. My question would be, well, let me preface this. So the reason that the design goal of Quick was to have a 3x anti-amplification limit was in part due to an analysis of the size of TLS certificate chains at the time that that limit was chosen. And I think you see there's like that Let's Encrypt, the 2 parts of that Let's Encrypt chain. I don't think that was a thing that was part of the ecosystem at the time. So like that was selected sort of as a trade-off between amplification limit and, hey, can we actually get through the whole TLS chain? And what we're seeing is the current TLS ecosystem doesn't work with 3, so network operators are roundly ignoring it, right? Which is correct, right? Like they're trading off sort of this abstract design goal for security for an availability goal, which is that's working as intended. What would that graph look like with respect to how much amplification we have if we had just set the limit to 4? I think that would actually, if the limit were 4, that graph would be green and not yellow, I think, if I'm reading the numbers right, which means maybe the advice to the Quick working group should be to, hold for document update that limit to 4x as opposed to 3x, right? Because it's a little bit more amplification risk for actually working with TLS the way it is.
Yes, so absolutely. The thing that I think the problem here is that we more or less have a static anti-amplification factor limit here, and it's not complete. So let's put it like that. how often will we have to change the anti-application limit if we see that deployments change? So maybe keeping the 3x anti-application limit will motivate better deployments in the future. So maybe keeping the 3x is the better way to do it, but I'm not sure how often we could otherwise or would have to change the anti-application limit.
I think it would happen once, and then ECDSA is going to get deployed for its own reasons anyway, right? So,
yeah.
It was just interesting. It's like, wow, this is super yellow, but that's an artifact of an arbitrary choice that was made in the working group. So,
all right, thanks a lot, Brian. I'm going to interrupt you guys here, and I apologize to Michael B in the queue because we have the next presenter ahead of him. Thanks a lot, Marcin. We're gonna switch to VIBABs. If you didn't get in, please talk with Marcin in the chat. All right, VIBAB, I'm sharing your slides right now. See if those come up. Do you know, Miria, do I need to do something?
Yeah, just grant the, next to his name. Sorry, I have connectivity problem. Next to his name, just grant him the slide sharing, and then you can select it.
I did that.
Okay.
I'm still seeing.
So you have select the right slides, and then we're done.
Oh, I see.
And it looks like he is selecting it.
Yeah, I revoked Marcin's. That's what I was missing. All right, VIBAB, can you say something?
Yeah. Am I audible?
Perfect. We can hear you.
Okay, we can hear you.
Slides.
Let's get the slides up here.
Okay.
There we go. All right, you're ready to go.
Okay. So yeah. Hello everyone. My name is Vaibhav. I'm a second year PhD student at Georgia Tech, and I'll be talking about my work on route variability in low Earth orbit satellite networks. And it's not just my work. I have had support of awesome co-authors, one of whom Ahmed, who is also attending the session, as well as my advisors Ketan and Adam. So let's get started. So I'm certain most of you would have heard about LEO satellite networks, especially with Starlink launching over 3,000 satellites in the past few years, with more than 10,000 of them being planned for the next decade. And these satellites have been shown to be able to provide high bandwidth and low cost internet access in rural as well as disaster affected areas such as Ukraine, Iran, Australia, and Florida. Further, a lot of recent work has shown that these satellites have the potential to outperform the current terrestrial networks. And the key reason for that is the ability of these satellites to form a network using the inter-satellite links, or the ISLs, through which they can route data to reach the destination. So let's take a step back and look at what exactly makes these networks. So fundamentally, every satellite consists of 4 laser links that will be used as the inter-satellite links, or the ISLs. And these links are arranged in a plus grid ISL topology. I'll explain this using the satellite in the center of this figure here. The satellite connects to its neighbors in the same orbit using the yellow colored intra-orbit ISLs, while it connects to satellites in its neighboring orbits using the purple colored inter-orbit ISLs. In these networks, paths are made up of 2 ground satellite links, or the ISLs or the GSLs, and 0 or more ISLs depending on the distance between the source and destination. For example, here I show you a path between New York and London. You can see the 2 GSLs here as well as the 3 ISLs. These networks have a highly dynamic infrastructure where satellites move at speeds of about 27,000 kilometers per hour. This results in a satellite being accessible for a maximum of 4.5 minutes. Note here that 4.5 minutes is the maximum time, since some satellites could be visible for even lower. So how does this affect networking algorithms, or why should we care about this new infrastructure, or the variability in this new infrastructure? So a key reason for that is fundamentally networking algorithms would assume stable paths and RTTs. For example, congestion control and adaptive video streaming would try to exploit this stability to converge to the capacity of the path selected. Similarly, traffic engineering algorithms would assume a stable ranking of paths to perform functions such as load balancing. So, like as I just mentioned in the previous slide, this is a highly dynamic network. So, some variability is to be expected. However, the scale of this variability would determine whether the current networking algorithms would require any modifications or if they can be used as it is. So therefore, in this work, we try to study the extent of variability in these networks. That is to ascertain whether this variability is small enough so that the current networking algorithms can handle that, or if it is large, which might require changes to these algorithms. So I'll briefly first describe the objectives of our study. I first look at route churn, which is defined as a measure of the frequency of change in routes between a source destination pair. And I'll give you a spoiler here that there is a lot of route churn. So we try to see if this route churn results in any significant performance gain, or in other words, is this route churn necessary? We also look at RTT variability, which we define as a measure of the variation in RTTs between a source destination pair. And as you can imagine, there is a lot of RTT variability. So we try to see if this exhibits any specific patterns or if this variability can be explained. So before getting into more details, first I'll talk about our simulation methodology. For this work, we look at the three constellations, Starlink, Kuiper, and Telesat, using their publicly available FCC filings. However, for this talk, I'll just focus on the first shell of the Starlink constellation, consisting of 1,584 satellites at an altitude of 550 kilometers. We use the satellite path models to predict the precise satellite positions at a given time step um, using the publicly available configurations. For all our experiments, we use the shortest path routing algorithm to minimize the RTT between the source and destination. We are able to do so by calculating the path length using the positions of the ground stations and satellites while using speed of light propagation. Also, I'll quickly add here that we do not perform a complete packet level simulation. We are just looking at propagation delay. We measure route characteristics for a total of 100 minutes while recomputing routes every second. And for our workload, we look at the 100 most populous cities as ground stations, which results in a total of nearly 5,000 source destination pairs. These 5,000 pairs, when ran for a total of 100 minutes, result in nearly 600,000 routes being observed. I'll emphasize here that these 600,000 routes or the 600,000 paths are the shortest ones at some point during these 100 minutes. So now let's look at the more interesting part, which is the observations that we had. I'm sorry, I had some animations, but the preloaded slides that seem to not be there. So yeah. So the first thing I brought up was how much route churn is observed. For this, we look at all the 600,000 paths that I just talked about, and we plot a CDF of the usage time and the lifetime of these paths in this figure here. If you look at the 1 minute mark here, you will see that while more than 80% of the paths exist for more than a minute, just about 30% of them are being used for that duration. This implies that most paths are being used for far lower time than what they exist. So this led us to wonder, like, what are the reasons for route churn? So fundamentally, there can be two reasons for that. The first one is that the path could cease to exist, or that there is a rerouting between valid paths for reasons such as lower existence of a shorter path. So we tried to see if we can characterize this route churn with these two reasons. So we plot another CDF. Here we look at the ratio between the path lifetime and the path usage time. If you look at the left side of this CDF, you can see that about 25% of the paths are being used for their entire lifetime, which means that in this case, route churn occurred because the path ceased to exist. However, on the other side of this CDF, you can see that more than 50% of the paths are used for less than half their lifetime, which means that in this case, route churn occur because of the existence of another shorter path. So essentially, this route churn would be justified if you're getting some significant gains in latency, and that is what we try to see next, whether the gains observed are significant enough, or in other words, is this route churn necessary? I'm sorry, is there? Um, I'm sorry, Dave, can I share my deck here instead? Because I think for this slide I needed the animation part.
Sorry, just go on for now. We're also short on time. We only have 2 minutes left, but like people can look up the version on the internet that is the PDF
Okay.
version on their own.
Okay, so
I think
briefly
we
I'll
have
talk through
7 minutes, I think, by the way.
So we try to see that if this route churn is necessary, and then we look at an example. Like, unfortunately, I can't go into the details here, but I'll briefly talk about a very specific point that I wanted to raise here, is that while in some cases route churn, as I mentioned, route churn in some cases occurs because of the previous path ceases to exist, while in some other cases it occurs because there is another shorter path. So here, I'll try to emphasize both the cases. Like, if you see the first, at the bottom, that is the first path that was selected by the shortest path routing algorithm. However, after about 16 to 18 seconds, that path ceases to exist, making the routing algorithm switch back to the blue path. After that, the red path becomes shorter than the blue one, making the routing algorithm switch back to the red one, only for the red path to cease to exist, making the routing algorithm switch back to the blue one, and then it switches to another path later. Essentially, what I'm trying to highlight here is that there are a lot of path switches happening here for different reasons, and like, I'm certain most of you would agree with me here that at least two of these path switches were unnecessary, especially after if I tell you that the latency gain while switching between the blue and red path and back was just 5 microseconds, the while the average RTT observed here was around 150 milliseconds. So it's like the latency gain is just about 5 orders of magnitude smaller than the RTT being observed here. And it's not just for this specific example, like what I had in this CDF below here. When we look at the ratio between the when we plot a CDF of the ratio between the minimum RTT and maximum RTT, we observe that in more than 80% of the cases, the latency gain observed is less than 25%. So essentially, we saw that there is a lot of route churn, and we also see that in most cases, the latency gain is fairly low. And it's not just latency gain, it's also application performance. Like, in the paper, we showed the impact of this churn on TCP, and it messes up all the different algorithms, or like all the like we tried 5 different TCP algorithms, and it messes up all of them. So, having looked at route churn, I'll go on to RTT variability. Okay, yeah, even this slide has some issues because
Yeah,
of
I think it would be great if you also can wrap up
Yeah.
soon, because we're running a little bit out of time. Sorry.
Yeah. So for this, we briefly we looked at we tried to plot heat maps with a point in the center as the source and 2,700 points globally. So the key takeaway here we observed was that while in most cases RTT does not change by much over time, however, in certain cases for certain points, or like based on the geographical structure, RTT can change by up to 2.5 times. We are able to show this for 3 different points, and some other examples as well. And then it's not just the magnitude. We also see that RTT variability exhibits a spatial structure, and okay, and we try to see if this can be explained, and we look at uh, like in the paper as well as in the slides here I had, I was going to show 2 examples. The first one is for shorter paths. For shorter paths here, what happens is over time the composition of the path can change very rapidly or very drastically, due to which the path length can change heavily. Like, one of the examples we show is that over a 6-second duration, the 3 paths being selected by the shortest path routing algorithm can have lengths varying by up to 2.5x, which is what we see in the circle here. While as you keep moving further away, there are other reasons that creep in, like the type of ISO, the type of links that are being used as well. So this is how, yeah, if you look at the paper, you will find more details here, or if you can look at the slides later. And yeah, with this, I would summarize the observations we had. The first thing we tried to look at was how much route churn exists, and if this results in any significant performance gains. We saw that there is a lot of route churn, and which in most cases does not result in any significant performance gain. And then we looked at how much RTT variability exists, and if this can be explained in some manner. We saw that RTT can change by up to 2.5 times while exhibiting a spatial structure. And finally, I would like to thank my co-authors again and our sponsors, and you can reach out to me at my email address here. Sorry for the mess up in this.
Big thanks to you for joining us in the middle of the night. Sorry for the trouble with the slides. We didn't check this carefully before. But you just published a paper last week, so people can read everything up and can reach out to you. And we have like a minute or two for questions. Jeff, do you want to come up, or you just take it on the chat?
Mary, we have one person in the queue. Yujan.
Yeah, Jeff is at the mic now.
Sorry, let me just ask the question rather than hitting the Q button because it's easier. What kind of service model were you simulating? Because when you've got this large mesh in the sky, you can either drop the packet back to Earth close to the original client and use the Earth infrastructure to get there, or you keep the packet in space close to the destination, which oddly enough means you get asymmetric routing in a round trip time because the Earth system presumably takes it close to the client before it leaks into space. But secondly, it actually amplifies the variance in RTT because that long space link is switching between the two inclined orbital patterns, you know, the satellites going left and the satellites going right, which actually amplifies the problem. I really wonder if those constellations are carrying a full route set or they're doing hot potato drop, which actually makes the entire problem far, far easier because you drop it back onto the Earth infrastructure and just do normal routing. Were you simulating the worst case?
You're right. So first, like the way Starlink works today is more of the hot potato drop, or the way it works is in the bent pipe mode, that any packet that the satellite receives, it will drop it to a ground station and then let the terrestrial internet infrastructure take care. But for this work, we are actually looking at the mesh that is there in the sky, in the space, that is using just the inter-satellite links. Like you only like this packet will hit the satellite and then it will try to reach to a satellite that is accessible by the destination, and that is what that is the model that we are using here. And
right, and I think that model has a massive impact on the results you get because you're keeping it up across the switching points, and while the propagation time is faster, speed of light in a vacuum, the sort of jaggediness and the dynamic rates of the curves, and I think you're also assuming a routing system that converges in 0 time because you kind of know where to go and you're not using dynamic routing, whereas I suspect dynamic routing would again make this worse than it need be.
Yeah, you're right. I mean, so this is why we first tried, like originally we wanted to look at a broader scope, but we found out that even if you know these things and you had an oracle telling you that, okay, this is where you're supposed to go, even then there can be a lot of variability, which is what we found to be quite interesting. And that's why we thought about sharing this before.
Thank you. Very helpful.
Okay, we have one more person in the queue. Chi, do
Hello?
you want to speak up? Yeah. Ah, yeah. Perfect.
Okay, my question is the setup really appropriate? Like, is the RTT or OSPF is recomputed in every second? Because you have the whole information on the global level, right? But in reality, each routing node, each router will not really have the global information, so that they will have those unnecessary churns, right?
So if I understood your question correctly, you're basically trying to ask that is recomputing routes every second necessary, or is that possible? Am I correct?
Yeah, I mean, yeah, it's maybe it's not a practical in reality, so there will not be your so-called unnecessary churns, right?
I mean, so again, like here we are doing this as a offline exercise, whereas in reality, because you have satellite path models, you have the configuration information, you can preload this information for like up to a day. Like for example, all the configuration by Starlink are valid for a day, so you can preload this for a day, for example, and do this. So it's more than the period of pre-computation. It is what the routing algorithm you are using and what factors it prioritizes. That is what leads to the churn here. Like, yeah, if you want, you can discuss it over the chat as well. So I think I'm out of time.
Yeah.
Thanks so
Thank
much.
you so much.
All right. Hello, everyone. I'm Robert from the RIPE NCC. Some of you know me as the man or a man behind RIPE Atlas. I'm not going to talk about Atlas right now, but instead a couple of things that we observe because we have Atlas, and it's deployed all over the world, showing us some interesting behavior out there. One would think that when you do measurements, the data that is coming back to you is going to be clean. Well, it's probably many of you know that's actually not true. And I think we reached the unclean state as soon as we deployed like the second probe or so. So we try to look at these things all the time. One thing that we see is middlebox behavior. There is, of course, all kinds of things that you can see. This is a beautiful example that we hit, I think last year. It was really popped up on our radar. And you know, when you're not prepared for such a thing, it kind of taints your analysis. So be aware that these kind of things happen. For those of you who cannot read the slides, the letters are small. This is a trace route going outwards, and the responding hop is the same for every hop. The IP address of the hop is all the same. The RTTs change. So this is a middle box middling with the packets. What's further interesting is that sometimes this happens on UDP and TCP, but not on ICMP. So if you think that on one protocol you get the answer, on the other you may not get the same one. So be aware this could haunt you. Something else. We believe what IP addresses can and cannot be used on the internet is known. Well, that's a good theory. The practice is slightly different. We discovered that on the trace routes that we do in some specific region, for some strange reason, this was close to Kazakhstan, we saw packets coming in from : /128, which is explicitly something that should not happen. There was a discussion on the RIPE Labs, some operators saying this is just what it is, deal with it, and then some others disagreeing with it. It can happen. If you will get the slides, those are actually links, so you can get to the articles describing this. Okay, a bit more controversial, 240/4, active debates, or somewhat less active nowadays, I guess, about whether that should or should not be used on the internet, reserved for future use or not. Fact is, some operators do use this. In particular, AWS is using that for intra-AWS routing. I think we have seen Verizon Business as well using it in their own network, which is quite interesting because if it's going to be ever categorized as usable on the internet, I don't know what will happen to AWS. That's would be fun. All right, now moving on to geolocation space. you think you know where France is, but let me remind you, this is where France is, okay? Just, if you happen to know where your vantage points are, just double check before you actually say, well, the US is this far from France. No, it isn't. I think it's true that France has the longest border with something like Brazil and not Germany. That might be wrong. In any case, so this is not an anomaly, but we go on to the anomalies. This is one. RIPE Atlas thinks, or at least we ask our host to tell us where the probes are. And some cases, that's not exactly true. What you can see is a probe in Brazil that can get to a German endpoint in less than 30 milliseconds. So that's actually not bad. What we do about this is we try to flag these probes so that the measurers can actually do something, whatever they want to do. At the minimum, just ignore these anomalies. But then, I think I skipped the slide. Let me just, maybe I didn't. That's fine. Excuse me. All right. Then finally, there is when you do know the geolocation and you're absolutely sure that your vantage point is there, and yet your probe or that vantage point can get to destinations which are far away in unreasonably fast packets. This happens as well. So this is a Russian probe trying to get to anywhere within less than 1 millisecond. And this is not, not the Russian problem. These probes exist all over the world. There are some which, whatever your question is, you're going to get the answer within a millisecond. And sometimes the answer is actually meaningful. So in this case, there's some content as well. So, be aware. I do not have conclusions. This was just, a random set of observations that we have. But if people would like to think together about what we can do in order to at least flag these, to let the measurers know that these things exist out there, just talk to me. I'm around. Thank you.
Yeah, thank you, Robert. So this was one of the 5 minutes heads-up talk that I promised you. That's just because Robert is around. He gave us some data, and I think Anna will actually tell us more about the problem now. So probably you want me to run the slides.
Yes, voice control, please.
Okay.
Hi, everyone. I'm Anna. I'm from the University of Aberdeen, where I do internet measurements, specifically for protocol standardization. So my work has been presented in various IETF groups along the years, and I've helped shape standards, particularly around transport. Next slide, please. So measurements are super useful for protocol standardization. It can tell us who work with standards whether or not a proposed standard has any barriers to deployment, or whether or not an existing standard is used. It helps us find various bugs that might exist in standards, and if you find a bug, then that's the first step towards fixing it, right? So measurements are useful, but in order to perform these measurements in a useful way, you kind of have to target a lot of the internet. The internet is absolutely huge, and that's the challenge here. It comprises billions of paths, and there's lots of diversity within it. You can have mobile networks, you can have satellite networks, and so on. So you have to target as many diverse paths as possible. So how do you do that? Next slide, please. Well, first you have to design your measurement campaign, and you have a few choices there. You can choose to generate packets and then throw them at the internet and see what comes back, and that's an active measurement. Or you can choose to observe traffic that already exists. That's a passive measurement. And then you can instrument your tests so that you control either one endpoint or both of the endpoints in your measurement, or maybe you're doing something from an in-network device. And then you have to consider which metric and at which level of aggregation you're actually measuring. So you can have performance metrics, or you can have something like a functional metric like connectivity. So you choose all of these things and you design a great measurement campaign. But there are, of course, some pitfalls. And this is what my talk is about today. And as an example, I'm going to use IPv6 extension headers. The measurements I'm going to talk about are going to be mostly active measurements and functional, so like connectivity tests. Next slide, please. So very brief overview of what IPv6 extension headers are. So IPv6 was designed from the start to be extensible, and you have these extension headers that should enable new functionality. They had a bit of a rocky start. So historically, you have different router architectures not necessarily supporting processing some packets with some extension headers in hardware. And for this historical reason, networks to this day, some of them drop packets with extension headers. Across the years, many different groups within the IETF have tried to measure extension headers. And if you look at the table there, you can see what appears to be conflicting results. But these results are not really conflicting. They essentially work together to tell a story. Next slide, please. So that's why I chose extension headers, because extension header measurement is pretty hard. And this is the kind of measurement where you're most likely to mess up in one way or another. And that's because the brokenness can exist in many different places. So some devices maybe don't support extension headers to begin with. Some of them maybe don't have the capacity to look deep into a packet to where your extension header is. Some maybe need to access upper layer protocol information and they can't get to it, or because an extension header is in the way. And finally, you have either by configuration or by misconfigurations, a network that actually filter them. Next slide, please. So how do you actually measure extension headers in a way that makes sense? Well, because they're not very widely used, you have to generate traffic with extension headers. So you generate traffic at your vantage point, you throw it across the internet, it gets to the destination, and maybe you get some feedback from your destination that your packet has actually arrived, and that's how you do an end-to-end test. So you can measure any property end-to-end, and you can work out if it actually works or not. But what an end-to-end test doesn't tell you is where the problem has occurred if something has gone wrong. So say your packet was dropped, an end-to-end test won't tell you where it was dropped, but you need to do path measurements for that. Next slide, please. So with that in mind, I'm going to give you some examples of where you can mess up your measurement. And I've divided this into 3 categories. I'm not quite sure why 2 of them are showing. Can you go to the next slide, please? Okay, 3 of them now. So the 3 categories are where we measure from, so your vantage points, where we measure to, destinations, and finally how we measure, methodologies. The examples are here. I'm going to go through them, but you can always refer back to the slide if something doesn't make sense. Next slide, please. Vantage points. So the pitfalls around vantage points relate around the lack of diversity in vantage points. So if you're going to do a measurement from a cloud provider, you'd better make sure that your cloud provider is transparent to what you want to measure. I can't remember the number of times I've started to measure something from AWS or from DigitalOcean, only to find out that the cloud provider was messing with the protocol that I was trying to test, and all of my results were garbage. So yeah, if you can, try multiple cloud providers and mix in active measurement platforms. Something like RIPE Atlas will give you connectivity to thousands and thousands of different vantage points. And they also have the advantage that some of these vantage points will be in edge networks. This will help you avoid this sampling bias pitfall. Now I'm going to move on to some examples. Next slide, please. Right, example 1. In this table here, what you see is the percentage of servers that reply to a packet that was sent to them with an extension header. So the set of destinations for each of these measurements wasn't changed. The only thing that is different here is the vantage point where I ran the measurement from. And as you can see there, DigitalOcean and Linode, when I ran my measurements from there, I received literally no answers from my servers. So that's because these 2 providers, they drop packets with extension headers, or they get lost in transit to the cloud provider upstream. Right, so this is still a good, valid measurement point. It's just that if you want to run a wide-scale measurement campaign to lots of destinations, this is not the place to do it from. Next slide, please. I mentioned a split between the core and the edge of the internet. And by that I mean, in general, the core of the internet is a lot more transparent to the traversal of different protocols. That is because you have less devices in the core of the internet that are likely to mess with your packets, so less middle boxes. Also, the more specialized the network, so like mobile and satellite, the more weirdness you're likely to get. So it's always good to have in a mix of edge and core paths. It leads you to think about the devices that your packets travel over. Next slide, please. Moving on to destinations. And the story here is more or less the same. You have to choose diverse destinations if you want to understand how things work, because the results may look different for different types of servers. Now, one thing that comes up again and again is the top 1 million domain lists. This is a list. It has top 1 million domains in it. You can resolve this list, and then you can filter it so that you only see unique IP addresses. And after that, you can run your measurements to those unique IP addresses that you found. And this gives you multiple web, mail, and DNS server targets that you can use. The problem with this list is that it's not diverse. Apart from this top list, you can also use crowdsourcing for your measurements. And this is great because you end up hitting a lot more clients in your edge. So then your client starts the measurement, and then, well, it contacts your server or your vantage point, and then you run the measurement back to them. These are great, but they're harder to reproduce. So that's something to keep in mind, because it can affect your ability to reproduce your own results, and it's the same for other people who might want to reproduce your results. Next slide, please. This is an example. I mentioned top 1 million domain lists are not very diverse, and you can hopefully see it in this table. This has 2 columns, and in the 2 columns you have the exact same data, except it's a per host view in your first column and a per AS view in the second one. And for years I've been presenting that results per host as opposed to per AS, but they might have been much more convincing if I'd actually gone and shown the per AS split. It's because you have many different hosts concentrated in ASs that maybe do something and drop extension headers. Right, so general point here for this slide, all the measurements that you do, you have to provide a per AS split. I'm going to move quickly through this slide. Basically, this shows, it's not my data, it's data from RFC 7872, and then some crowdsourced measurements from APNIC. You can skip ahead too. And one more. These are all essentially examples to show you that if you choose different types of destinations, then you can understand the picture a bit better. Because if you think about it, some of the servers that you target might be behind specialized infrastructure. So if you look at web servers, they might be behind a CDN or behind a proxy or load balancers and so on. Or if you're going to clients in edge networks, then you might have edge network specific middle boxes in the way, and so on. So infrastructure may look different for different server types. That's something, that's the key point here. Next slide, please. And finally, we move on to methodology. Here, the pitfall is to not approach the problem from all of the angles that you can approach it from. So it's always good to combine measurement approaches. You can combine passive and active measurements if you can, and that will help you understand things better. Another thing to keep in mind here is that it's always useful to compare your methodology and results to anything else that has been done in the field. And in fact, I would recommend to any researcher to try and first reproduce results that exist, because this kind of tends to help you get out of the way all of those silly issues that you might find when you set up your experiment. And something else that I would advise is to open source your data, because this allows other people to A, validate it, and B, build upon it. Next slide, please. And in terms of performing measurements, of course, you should always measure multiple upper layer protocols. because sometimes the choice of upper layer protocol will influence traversal at the network level. And then don't necessarily assume you understand how the internet works. There's lots of balancing in there, and there's lots of weird middle boxes that do weird things, as Robert pointed out. Next slide, please. So the final two examples are around protocol differences. So this is just a slide to show you that I've measured loads of devices in edge networks, and it looked there like there's a split between UDP and TCP. So this is an opportunity to understand why TCP traversal for TCP is different than for UDP. It's because lots of edge devices might mess with TCP, and then you can start thinking whether or not there's a link between those devices and traversal. Next slide, please. And then I say the best example for last. Load balancing. It exists in the internet, and you can measure it with something, well, the main tool you can measure this with is Paris Traceroute, and I'm sure many of you are already familiar with this. Paris Traceroute is a tool that attempts to find load balancers between a source and a destination by running multiple trace routes, and in between each measurement, it varies some of the header fields. So in that first picture here, you can see that I measured a source and destination with Paris Traceroute, and I find 4 different paths. I find at least 2 load balancers in this network, and that's great. But then if I repeat this measurement, except instead of sending regular packets without extension headers, and I sent packets with a destination option extension header instead, all of that load balancing is completely lost. I no longer detect 4 paths. And that's probably because load balancers, these ones in this particular example, they were using byte offsets in order to route packets onto different paths. But all of that is lost because now you have an extension header in the way. Next slide, please. This is just a close-up. So next slide, please. And conveniently, this is my last slide. To sum it up, always try multiple approaches for the same measurement, use multiple vantage points and destinations, and never expect anything on the internet really works the way you think it should. That's it. We can move on to taking questions. Thank you.
Thanks a lot. We actually don't take questions, but there's a lot of discussion in the chat already. Okay. And this was a talk about more methodology point of view. So if this group wants to work more on this, then I would also be excited to see some more discussion on the mailing list. Thank you very much for bringing it. And as you said yourself, like the summary on the chat is kind of, don't assume that you understand the internet. So that's a good takeaway. And we move on. Simon, you also should probably request sharing.
I think he did that with video, and I accidentally closed that. So Simon, you'll have to request video again too. There you go. And can you request to share your slides? Oh, you did that. Thank you. Okay, you ready? Maybe I just see still video. Simon, can you hear us?
Yeah, okay.
Okay,
there, we got you now. Okay,
you.
ready to go.
Perfect. Go ahead.
Okay, you can hear me and you can see my slides.
Yes.
Oh, great. Yeah, hi. So my name is Simon Sandberg. I'm a PhD student at Karlstad University, and I'm here today to present some work we've been doing at Karlstad University in collaboration with Red Hat on enabling efficient continuous latency monitoring by using eBPF. So as you're hopefully all aware, network latency really matters. It has a large impact on the quality of experience for basically any type of interactive application that runs over the network. That's true already for many of our current applications today, such as this video conference in right now. But it will become even more important if we look towards future applications, for example, AR and VR, and many of the applications envisioned for the tactile internet will require low and consistent latency in order to be possible to realize. So we need good tools to continuously monitor network latency in order to determine if our networks can actually support these different applications. And the continuous part here is very important because network latency can very rapidly change, giving issues such as jitter. And you can't really detect this if you're only occasionally probing the network. So if we look at the tools we have today for monitoring network latency, most of them rely on actively probing the network, such as, for example, Ping Mesh and the RIPE Atlas measurement platform. Now, these are all great tools, but the problem with them is that they don't actually capture the application perceived network latency. They just give you the latency that these probes experience. So as an alternative, we can use passive monitoring, where we are able to infer the network latency directly from application traffic. And some of the tools that we have today that can do that includes Wireshark and the passive ping or p-ping application. Now, the really nice thing with these tools is that they do actually give us the application perceived network latency because they operate on actual application traffic. But the problem is that they rely on packet capturing to do so, and this comes with a lot of overhead, which means that they often don't scale that well to the high packet rates that we can encounter on modern multi-gigabit network links. So our work is very heavily inspired by this passive ping or p-ping tool. So let's just take a very quick look at how it works. So the basic idea behind p-ping is basically to match up packets with their replies and then calculate the RTT by taking the time difference when you saw the original packet and when you saw the reply to this packet. And p-ping does this by using TCP timestamps, where each TCP header will contain a TSVAL and TSECR field. The sender will put its own timestamp into the TSVAL field, and the receiver will echo it back in the TSECR field. So you can simply match the value in the TSVAL field with the value in the TSECR field to match up by packet and reply and get the RTT that way. So we think that this p-ping tool is really nice, but as mentioned, it doesn't really scale that well to high packet rates. So our proposed solution here is an evolved passive ping or EP-ping, where we take logic very similar to that of p-ping, but we implement it directly in kernel space by using eBPF. And by doing this in kernel space, we avoid the need of having to clone the packets with packet capturing, because we're able to operate directly on the packet buffers in the Linux network stack. And we also don't have to send the entire packets to user space. Instead, we only have to send the RTTs that we compute with this passive monitoring in kernel space. And now I realize that most of you probably don't know what eBPF is. So the very short version is that eBPF is basically a technology that allows you to attach small custom programs to various hooks in the Linux kernel at runtime. And by doing this, you can then modify the behavior of the Linux kernel without having to recompile the kernel or load any kernel modules. So in our case, we've basically implemented this passive monitoring logic in eBPF programs that we've then attached to the very early parts of the network stack. So, did we see any performance gains from moving this passive monitoring logic to kernel space? Well, to test that, we used a rather simple setup consisting of a sender and a receiver that were connected via a middle box, which then just forwarded the traffic between these two end hosts. We then sent various amounts of iPerf flows from the sender and then passively monitored the round trip times from the middle box, either by using the original p-ping or our EP-ping program. And we then also compared the performance against a baseline where we didn't use any passive monitoring at all and just forwarded the traffic. So the results you see here are when we had 10 concurrent iPerf flows, which was when we observed the highest throughput on our testbed. And as the leftmost graph shows, we basically observe the same throughput in all cases, regardless if we were using passive monitoring or not, because the end hosts were the bottleneck. So roughly 55 gigabits per second of throughput regardless. But if we move to the middle plot, we see the CPU utilization on the middle box. And as you can see there, this passive monitoring does have some overhead. However, the overhead for our EPPing tool is only about a third of the overhead compared to the original peeping. And if we move to the rightmost plot, EPPing operates on in line with the network kernel or the network stack in the kernel. So it sees every packet that the kernel actually handles. While on the other hand, peeping operates on these clone packets from the packet capturing. And the packet capturing is not able to keep up with the high packet rate here. So the original peeping only handles about 6% of all the packets that this machine actually forwards, despite its much higher CPU utilization. Now, in this previous test, the end hosts with a bottleneck, which means we weren't really pushing this middle box or our passive monitoring solutions to their limits. So we moved the bottleneck to the middle box by eliminating it to using a single CPU core. And this CPU core was then fully utilized even when just forwarding the traffic, and any overhead from this passive monitoring then resulted in a lower forwarding rate. So first off, I just want to point out again that the original peeping here misses most of the packets. So we actually have two lines for it. The upper dashed orange line shows the forwarding rates of the middle box while running peeping, while the lower dotted orange line shows the rate at which the peeping process itself was actually monitoring packets. So it's only actually handling a small fraction of all the packets that are forwarded here. If we look at the performance for our ePeeping tool, which is in the green line, we see that at a few concurrent flows, it performs much better than the original peeping. However, as the number of concurrent flows increase, we also see that performance drops, and at 1,000 concurrent flows, the forwarding performance is not really any better here. But as mentioned, ePeeping runs on every packet, so we're actually at 1,000 flows monitoring packets at roughly an 18 times higher rate here than the original peeping does. And the reason we see this drop in performance is basically that the algorithm that peeping and ePeeping uses results in more RTT samples the more concurrent flows we have. So at 1,000 concurrent flows, ePeeping is trying to report roughly 130,000 RTTs per second. And this comes with quite a lot of overhead that the original peeping sort of accidentally avoids by missing most of these RTT samples to begin with. So we then also looked a little bit at how to deal with all these RTT samples by doing some in-kernel sampling and aggregation. And the blue line in the left plot here basically shows the same performance as the green line in the previous plot, which is when ePeeping is trying to report every single RTT value. And then we basically reduced the frequency that each flow could report RTTs. And those are the lines above, which then show that obviously helped a lot with performance. But by doing sampling, we of course also lose some granularity in our measurements. So we also looked at doing some in-kernel aggregation, where instead of reporting every single RTT value to user space, we aggregated them into a histogram that we only periodically reported. And that's the right-hand side plot, where even the blue line, which is for reporting all of the RTTs, we see that the overhead now is not nearly as affected by the number of flows, and with just a modest amount of sampling, we can largely get away from this drop in performance. So to quickly recap, what we've basically done is that we've implemented continuous passive latency monitoring directly in kernel by using ePPF. And by doing this, we've been able to drastically improve the performance compared to packet capturing solutions such as peeping, being able to monitor packets at over an order of magnitude higher rates. In our case, we show that we were able to handle over 1 million packets per second, corresponding to over 10 gigabits of TCP traffic on a single core. And we also looked at using some simple in-kernel sampling and aggregation to reduce some of the overhead that was associated with having to report a large amount of RTT values. So right now we're currently working on further improving this in-kernel aggregation of RTT values. And we also want to evaluate EPPing from an ISP vantage point to get a more realistic traffic load. And in the future, we are considering adding support for additional protocols, such as, for example, QUIC by using the QUIC spin bit. Finally, I just want to mention that EPPing is open source. So if you're interested, please go ahead and try it yourself. And if you have any ideas for how we can improve this tool, please reach out to us. So thank you for your time and attention. And if you have time for any questions, I'll do my best to answer them.
Thank you. We would have time for like one very short question. But we can also just move on because we're short on time. So thank you for presenting. That was very interesting. And I hope people provide you more comments in the chat.
Yep, thank you.
So next we have Martino.
Hello, can you see and hear me?
We can hear you. We're still waiting for your slides.
Okay. I asked to share my screen.
We can try that.
Okay.
It still shows us as okay. I stopped the slides.
Yes, I really want to share my slide.
So the slides are already uploaded, sorry.
Okay.
And I think Dave is now sharing them for you.
No, I
know
meant
you
that I
did-
just stopped the slides we
sorry.
had before you.
Yeah, now you're sharing your screen.
Yes.
But we could also use the uploaded slides.
Okay. But I think
Why don't you go
that's
with this,
fine.
Martino, if you could? Yeah.
Okay.
Okay, that works.
Can you see the slides?
We can.
Properly?
We can. Yep.
Okay.
You're ready. Thank
Perfect.
you. Go ahead.
Okay, good morning, actually, good afternoon, everyone, and thank you for inviting me in this meeting. I'm going to present the paper measuring the performance of a cloud private relay that was presented the week before in the PAM conference. So let me first introduce a bit the context very quickly. The context of this paper is about privacy and web. And so let's see a bit the steps toward encryption that was taken during the last years. On the beginning of the internet, almost any protocol field wasn't clear. And so this was a problem for security because passwords and credit card numbers weren't clear. For privacy, because your ISP could observe your traffic, see the website you visit, and also your interest. And so, starting from 2010, we observed a trend toward encryption with more and more encrypted protocols like TLS, and more protocol fields got encrypted. Let's see briefly how the picture changed from the beginning of the web. On the beginning of the web, we had HTTP, which was unclear with unclear URLs and unclear client-server IP addresses that are needed for routers to route packets. Then with HTTPS and TLS, the HTTP URL is encrypted, but the domain name is still unclear because it is available in the server name indication field of TLS, and still IP addresses are visible to the network. Now we have HTTP 3, TLS 1.3, and QUIC, and the picture changed again. The HTTP payload is encrypted. Now you can also encrypt the TLS client hello and the server name indication using the TLS extension called TLS encrypted client hello. But client and server IP addresses are still unclear. And if you really care about your privacy, client and IP addresses can be a problem, because looking at the server IP address, your ISP can more or less understand the websites and the portals that you visit. And conversely, a website can track you by looking at your client IP, even if you delete cookies and you delete all this information. So the classical solution to this problem has been virtual private networks that are there since the 90s. IPsec was standardized in 1995, and one of the most popular VPN-like services is Tor. With a VPN, your ISP cannot understand the website you are visiting, and the website cannot get your real client IP address. Now we have the Apple way for VPN, which is called the Cloud Private Relay, which was launched in 2021. It is included if you have an iCloud Plus plan, and is a VPN-like service directly integrated in any Apple device running macOS and iOS, and is also very easy to use because it's integrated in the US. You just go in the settings and you enable it. Private relay can be very interesting to study for several reasons. First, because it can become really widely adopted because it's very easy to use, and there are a lot of macOS PCs and iPhones, and also these can really change the traffic mixture of the web. This recent INC paper already foresees a tectonic traffic shift due to private relay. Also, private relay can be interesting to study because it relies on a very large infrastructure because it is based on Akamai, Cloudflare, and Fastly. And also, Apple declares that there are more than 200,000 subnets hosting a relay of this private relay network all around the world, looking at this image again from the previous mentioned IMC paper. Private relay can be also a problem for geo-blocking services because it's harder to get to understand from where a user connects when using a VPN. Private relay can be interesting also because it has a kind of novel technical operation. First, because it is based on a two-hop architecture. The traffic passes through two proxies before reaching the server. And also because it is the first VPN based on QUIC, and it also implements some novel features of QUIC that we will briefly mention next. First, let me explain very quickly how this multi-party relay architecture works. In this multi-party relay architecture, you decouple the network identity, which is notably the client IP, and the internet usage, which is identified by the server IP, in this way. The traffic from a client passes through two proxies before reaching the destination server. And the client establishes a first tunnel towards the first proxy, a second tunnel towards the second proxy, and then it uses this tunnel to serve the packets to the destination. The first proxy is managed by Apple and can get only the client IP address, but doesn't know the server IP. The second proxy, managed by Akamai Cloudflare on Fastly, can see clearly the server IP address, but do not know the client IP address. So there is no entity that at the same time knows both client and IP address, and this enhances privacy also from the VPN point of view. As I said, this is a first attempt to have a VPN based on QUIC, but QUIC had to be modified a bit because there are some problems. The main problem is that having TCP in QUIC or QUIC in QUIC entails having two levels of encryption and two levels of reliable protocols, and this can be a problem. So the first problem to solve was to avoid having two nested instances of reliable protocols, and then also with the TLS and HTTPS, you typically use the connect when you use a proxy. With QUIC and HTTP3, there was not connect equivalent, and so the solution was to use this recently standardized extended connect for QUIC. But let's come to issue one. As I said, having two nested instances of reliable protocols can be a problem because you expect long delays and frequent connection aborts. So in this case, the solution was to use a quick and reliable datagram extension standard that was standardized really soon, also called MASC. In MASC, you disable retransmissions in the outer quick connection, and you keep retransmissions only in the inner quick connection, so that there is just one instance of reliable protocols, and you avoid all the problems that could arise. So let's see the goals of our work. Our work is about studying the performance of private relay. So we wanted to study if there is a performance penalty using private relay. So if you experience slower throughput, downloading files takes more time, or web pages load more slowly. To this end, we deployed a small testbed based on 3 macOS PCs, one in my city, Trieste, one in Lyon, and one in Honolulu. Each PC was connected via Ethernet to the internet and had a paid subscription of a cloud private relay. We ran 3 sets of experiments. First, a throughput measurement using an automated version of the OCLA speed test portal to understand which is the download and upload throughput when using private relay. Then we tested downloading a large file. So how fast is private relay when you download a large test file, in this case a 1 gigabit file hosted on the Hetzner CDN. And finally, we tested web browsing, visiting the top 100 websites for each of the 3 countries using browser time, which is an automation toolset to automate the visits to a website using Safari. And we measured, among all, the page load time, which is how long a page takes to load, and so the time between the first and the last HTTP request, because a web page is composed of many objects that must be retrieved. And also, page load time is a good metric because we know that it is correlated with the user's quality of experience. So let's briefly see our results. Let's start from throughput. We observed that iCloud Private Relay in download is not as fast as the native network. Here you see that the red lines are more shifted to the left than the blue lines. Also, we noticed that the performance really varies on the proxy, on the relay that is chosen by the system when you turn on Private Relay. In France, if the system chooses a Cloudflare relay, you go much slower than with Akamai. And in the US, Cloudflare was much faster than Akamai. So the infrastructure still has some issues related to the chosen server or relay. In upload, again, private relay is not as fast as the native network, as you see in these plots, except for US, because our testbed was located in Honolulu, and there the problem was a bottleneck in the uplink, and so the throughput was limited to 25 megabits per second. Regarding bulk download of a large single file, so a single very long HTTP request, there is no clear winner. In Italy and in the US, it appears that private relay is lower, but in France, actually private relay appears to be faster than using the native network, and we suppose that this is due to some routing issues, to some selection of CDN nodes. Finally, regarding page load time, using iCloud Private Relay, we noticed that page load time is larger, so web pages take more to load. The increase in time is about 60%, depending on the website, but still it's sizable. So web pages load slower, probably due to the extra round trip time imposed by all these routing through relays. But there is a sizable penalty when using private relay. So to conclude, we observe that private relay moderately impacts performance in a negative way, and this also can be tolerable because it is the first attempt of making a VPN based on QUIC and using some novel features of QUIC. But there are still some aspects to study that we plan to study in the next future. So the implications for geo-blocking. As I said, the private relay, in general, massive adoption of a VPN can create problems to geo-blocking services, and also a massive adoption of private relay has a cost in terms of computing resources to double encrypt this traffic that must go towards these encrypted tunnels. And also there is an energy problem because you additionally encrypt traffic and this consumes some energy. I think that's all. I hope I saved some minutes, and I'm happy to answer any question. Sorry for this strange effect.
Thanks, Martino. We have 2 questions, Tommy.
Yeah, thank you for doing the measurements. I appreciate. I'm Tommy Polly from Apple. I worked on private relay. So I want to specifically talk about the speed tests. I think there's definitely implications of where the speed test servers are, et cetera. But I'm curious, when you're doing the Ookla speed test, do you know if it's doing the multi-flow or the single flow mode? Because by default, it often does a multi-flow.
Yes, I think multi-flow.
Got
This
it.
is the standard browser speed test automated using Selenium.
Yeah, great. So, I mean, it's interesting. So when you do a bulk download, that's generally a single flow. And I think, as you see, it's generally comparable. What we have observed, so private relay, when you're running Ookla speed test through it, is putting it through a single quick tunnel. So it's essentially, from the network's perspective, one UDP tuple. On some networks, like when we have networks that are, let's say, like a wired Ethernet with a gigabit, we're able to get gigabit throughput with and without. It's the same. And often what we're seeing is actually that there's per flow, per 5-tuple load balancing or other network slowdowns that are happening. So one of the things we're looking at is MP quick as a way to expand the number of flows. But I think I'd be curious to see more experimentation with single flow versus multi-flow mode and trying to find different types of networks and identify networks that are doing per socket throttling versus allowing a single socket to take up the full bandwidth.
Yes, thank you. I think that's something that can really happen. If there is some path that has a link bond which is per flow load balanced, probably the single outer quick connection cannot get a large throughput. Also, we observed that there is some issue in the choice, not some issue, some impact in the choice of the speed test server, because with the private relay, you choose a speed test server which can be farther away than when using a native network.
All right, Eric Kinnear, also from Apple. Thank you for doing a bunch of this work and for bringing it here. I think we'd love to chat more offline as well and see if we can help collaborate. I had a question about some of the actual page load metrics and kind of where did you start measuring the page load in the graph that you showed? Because we have some metrics from more than 3 max. And they seem to think that France is like faster in general for page loads rather than slower. And so it'd be interesting to hear some of your speculation about why that might be faster and maybe compare some notes and see if we can help move things forwards in that space. So thank you for doing this.
Okay. Thank you.
Okay, thanks. Thank you, Martino. We're completely out of time. We're over time, actually. Thank you for presenting here. We have this last heads up talk. Mocha is just presenting her new measurement work in 2 minutes.
Mocha, 2 slides, 2 minutes. IPv6 only resolvers, what is stopping them? So if you have an IPv6 iterated resolver that only has an IPv6 address, you can't resolve all names because they are IPv4 single stack authoritative name service out there. Next slide, please. So I did a measurement trying to resolve 1 million domain names using IPv4 only iterated resolvers and IPv6 only iterated resolvers. So for success rates for all domains, I was able to resolve most domains with IPv4 only resolver, but for using an IPv6 only resolver, I was only able to resolve 64.1 of all the domains. And that makes sense because IPv6 deployment is still being done. Not everyone has IPv6 connectivity, not everyone has IPv6 address space. But what I thought was interesting was I saw the domains with quad A records. So I tried to resolve domains, and I found 24% domains that has quad A records using a IPv4 only iterative resolver, but I was only able to find 22.5 with an IPv6 only iterative resolver. So that is 93.8% success rate. It is not 100%. So domains with quad A records, they are supposed to have IPv6 connectivity, IPv6 address space. Maybe their authoritative name servers are using different services, but it would be nice if this one was 100%. Sorry, next slide, please. Oh, this is my third slide, sorry. So these are some of the these were some of the domains I could not resolve with an IPv6 only iterative resolver that has a quad A record. Next slide, please. Oh no, fourth slide. So this is me trying to resolve wikipedia.org. It has a quad A record, but its name server ns.wikimedia.org does not have a quad A record. Sad. Next slide, please. Oh no. So Harvard.edu, Harvard has a quad A record, but when I try to resolve Harvard.edu's DNS authoritative name server, this is me asking m.edu.services.net. I can get the IPv4 address of the authoritative name server from the additional section, but it did not tell me about the IPv6 address. Very sad. So so there are domains that have quad A records, but they are not resolvable by IPv6 only iterative resolvers. Not being able to resolve all domains makes sense because IPv6 deployment is not 100%, but for domains that have quad A records, it would be nice if I could resolve them with my IPv6 only iterative resolver. Thank you.
Thanks a lot. So sorry for running over time. I hope you enjoyed the session. Thank you everybody for joining online, and see you next time.
Thank you. Have a good week, folks.
Thank you.